Hello, everyone. I'm Chip. I'm very excited today to be hosting one of my favorite engineers ever, Wes McKinney. I have always been a fan of his work, like who isn't? So he's a creator of pandas, Apache Arrow, and Ibis. And I find it's really hard to create one thing that is popular, and it's so much harder to create multiple things that are popular. So I think it's fair to say that if you're doing anything with data today, you're probably using something that Wes created. So at the same time, I'm seeing a lot of changes in the data systems. So first, we see that like AI is now everywhere. We cannot talk about data without AI, and we cannot talk about AI without data. So we see a lot of movement, like more companies want to use AI, and they need to get the data system in order. And now the data system has to support data of different format types, and not just structured data, unstructured data, and how to be able to query unstructured data just as a way we do structured data. And the other direction is that composable data systems, we see a lot of movement of like big data players adopting like open data standard. Just last week, we saw this that Databricks acquired Tabular for $1 billion, and then Snowflake just before that supported announced Polaris. And then we see many people adopting Apache Arrow, and we saw that also people are adopting Ibis. It's like who would be a better person to discuss what the future of the justice system could look like than Wes McKinney. So I'm very, very happy that he was very generous to like accept our invitations. So today we're gonna have Wes and we have Chloe who's gonna be helping us with the moderations of the conversations. So the event is live streamed on YouTube. You can watch it later, but you can also join the discussion on Discord. So you can find the Discord link on the video description. So, okay, here's our guest, Wes. Please, um, we can start the talk.
All right. Thanks for having me. Well, I don't want to wear you all out with too many slides. I've given a bunch of talks in the last 6 months to help spread the word about all the different things that are going on in composable data systems and some of the history about how these pieces started to come together and how my involvement in working with these different open source communities. But I understand that many people on the call maybe haven't seen those talks, so I'm going to go through a few of those key concepts, which I think will be really useful to set the context for the rest of our conversation and answering your questions. So let me see if I can share this window here, do the Google slideshow. Um, Looks like that's coming through all right. Um, yeah, so I want to give just a little bit of an overview of like how I ended up working on these types of systems and give a little bit of a history of pandas and other things in the data science ecosystem. As Chip mentioned, most people know me as the creator of the Pandas library. I wrote the book Python for Data Analysis, which has been a really popular reference textbook for learning how to use Pandas and getting started doing data science in Python. But I've also been pretty involved in the Parquet community, and I co-created the Apache Arrow project, which I'll talk a little bit about today. And I also created the Ibis project, which has been growing rapidly and is serving as a tool to bridge the worlds of disparate SQL systems and making it easier to access hardware accelerated computing from Python. So I wear many hats. I'm a software architect at Posit. I'm also a co-founder and a senior advisor at Voltron Data. I have a part-time. I'm a part-time VC, so I operate a small venture fund where I invest in many data infrastructure companies and developer tools that enable data scientists and next generation machine learning and AI. I was an angel investor in Tabular, so I've been kind of involved in Tabular since the start, and a huge fan of everything that has been going on in the Iceberg ecosystem and open standards for data lakes. So it's definitely it's amazing example of like the how important these open standards like Iceberg have become to the whole data ecosystem. So our company, Voltron Data, if you haven't heard of it, is focused on unlocking the potential of GPU accelerated analytics for large scale workloads. We also develop and support the Apache Arrow and Ibis communities. I need to add Ibis to this slide. We have a bunch of open source partnerships. We've raised a lot of venture capital. We're growing really fast, and so if you're interested in hardware accelerated computing, the Voltron Data website has amazing resources for learning more about the details in the composable codecs. So I encourage you to go check that out. If you've never heard of Posit before, that's because it used to be known as RStudio, and in 2022 rebranded to Posit to reflect that it has become a polyglot, language agnostic data science platform company. And I worked actively with Posit going all the way back to 2016 when we created the Feather file format for Python and R, which was one of the first production applications of Apache Arrow to make it easy to share data frames at high speeds between Python and R. They have been very involved and helpful in building out this ecosystem. The Pandas project, I'm sure many people on the call use Pandas or have heard of Pandas. Development of that project goes all the way back to 2008 when I was working for a quant hedge fund. We were in the midst of the great financial crisis, maybe not the best time to create new software projects, but perhaps like the stress and uncertainty of the time led to a lot of innovation. I was able to open source the project at the end of 2009, and then in 2012, I had dropped out of grad school to work on Pandas and got a book deal to write the first version of my book. And in 2013, turned over the Pandas project to the open source community, where it has been community owned for the last 11 years, which has been great because it's freed me up to be able to work on other open source projects and help grow, a bigger and more productive open source data ecosystem. So the role that Python has served in the data stack is as the essential data access and in-memory data manipulation layer. It's hard to believe, but if you go back to 2010, it just wasn't that easy to load data files into Python and work with them in the same way that you would in other programming languages. And so part of the reason why Pandas got so popular is that it made it easy to just read your data and do really basic things in it. And particularly when you needed to use scikit-learn or eventually TensorFlow and PyTorch and other machine learning projects, Pandas would always be involved as the essential on-ramp for data into the environment. And so that's part of why it's gotten so popular and has been part of its staying power. And I think it's also, Pandas has become the Swiss Army knife, providing thousands of different, little pieces of functionality to serve, all the disparate needs that arise in the course of doing data work. Pandas wasn't the only thing that caused Python to become so popular. I think there was a confluence of many projects that had to happen all around the same time. The foundation of numerical computing and NumPy and SciPy. But then we were lucky that Python became the language of machine learning and AI. So I think the open source projects like Pandas and scikit-learn were a big help. But then having Google and Meta choose Python as the language where they would build their AI frameworks certainly cemented Python's role as the language of AI. But if you go back about a decade ago to the big data world and the world of large scale data processing, ETL, and data management, that first wave of data systems were all very Java and JVM centric, and nobody had thought very much about how to build high quality Python interfaces to these systems. And so this was a problem that I started thinking a lot about and looking like, hey, how can we, tie the room together and make it easier for people to use Python to build interfaces to these systems and keep all their work within the nice Python environment that they're used to, the Jupyter Notebook and all of the Python tooling that we're all familiar with. But there were a lot of really basic problems, just moving data around and getting data in and out of systems, connecting Python, executing Python code inside other systems was really difficult. And one of the things that we decided to do was create this project Apache Arrow to serve as a language agnostic data fabric or data connectivity layer that serves simultaneously as a really efficient data structure for high performance analytics, but also a language independent data representation, which can be used to transport massive quantities of data across language boundaries within a single machine, as well as transporting large data sets within distributed systems. And it turns out that making networking performance and distributed systems performance faster has been a big theme of the engineering work that we've had to do in the last 10 years to be able to scale to the challenges of utilizing modern hardware. And so this is kind of a big theme of the Apache Arrow ecosystem. And many people have asked, well, why did something like Apache Arrow take so long to come around? Why in the middle of the 2010s? And a big reason was that we all saw hardware changing really fast around us, particularly in the early 2010s. If you look at core counts in servers, this chart is a little bit out of date, but it used to be that there weren't that many cores in servers. But in 2023, you could get a 128 core server. Now AMD has 96 physical cores on a single socket. So in a dual socket server with hyper-threading, you can get up to 384 threads of simultaneous computation. Disk performance has also seen more than an order of magnitude improvement in read and write performance at the IOPS level. Like IOPS have seen 2 orders of magnitude improvement or more in the terms of the number of IO operations per second that you can perform. And then networking has increased also at an exponential scale. And all these systems were built prior to this period of exponential improvement in hardware that we're seeing. Particularly when you think about how Moore's law has been broken through, and we're seeing exponential gains continue in GPUs and in ASICs and custom silicon. And so it isn't practical for every system to independently figure out how to leverage all of this high performance computing and next generation hardware. So we started to say to ourselves, well, what if we could create technology that would make it easier for us to build reusable systems that leverage that squeeze all of the juice that's possible, all the juice possible out of these different hardware systems: computing hardware, GPUs, high performance disk drive, shared memory, networking, high performance networking performance, and InfiniBand. And at the same time, the code that we write in each programming language, it looks very similar. So in Python, we might write this pandas code, which reads a CSV file or reads data from a SQL database and performs some DataFrame operations. Or you could write the very similar code in R that does basically the same thing. In many different SQL engines, you could write similar code in SQL that does the same thing. And so my motivation and interest in the Arrow project was to work towards building this, what I described in 2017 as a shared data science runtime, basically a reusable modular platform of computing technologies that can be used portably across different programming languages, and where we can facilitate collaboration across a very heterogeneous data science, machine learning, and AI ecosystem. So that rather than having everyone figuring out on their own, like, how do we get the most out of modern GPUs and how do we get the most out of modern networking, that we have these pieces of reusable technology that we can collaborate on and make really, really awesome. And it turned out that Arrow was a key technology that unlocked a path to being able to do that. And we've spent a lot of the last 8 or 9 years both making Arrow a mature and stable foundation for doing that, and building kind of the peripheral ecosystem of open source projects that are built on or compatible with Arrow. I had a lot of help along the way. Early on, I set up a industry consortium funded by some financial firms and hardware companies like NVIDIA and Intel, financial firms like Two Sigma and Bloomberg, as well as Posit was an early backer and a key partner in making this possible. And so in the broader stack of big data systems, in the early days, in the Hadoop era, in the late 2000s, early 2010s, everyone was really concerned with, well, all we need is for things to scale. We aren't necessarily so concerned with efficient hardware utilization, but then again, most applications are I/O bound because disks are really slow and networking is really slow, and so there was less energy put into this really specialized computational systems development. And then after that, we moved to more of a distributed in-memory computing model with Spark as like the first major system that introduced, mainstream distributed in-memory computing as RAM on servers got bigger. But at the same time, software vendors also shifted from building proprietary systems to taking open source projects and delivering them as software as a service solutions. And so it took a lot of years for these ideas to percolate and for everyone in the open source community to converge on the necessity of building these modular reusable components that solve these problems really well and that can be reused so we don't end up with 12 clones of the exact same thing. So fast forward a bunch of years, and the way that this is kind of shaken out in the thinking about the peripheral stack of technologies around Arrow, we have data lake access and interoperability through open source file formats like Parquet and Orc, which I'm sure you're all familiar with. Of course, we've put a lot of energy into language interoperability and building protocols and standards for connecting different programming languages together with Arrow, as well as some things like accelerated database access to because databases they speak SQL, but they're not really programming languages, but they're still an important part of that language interoperability stack. More recently, we've seen a major shift towards building fast embeddable query engines. And through working, large part, we've really been a leader in this at Voltron Data in defining these new interoperability standards for databases like ADBC, which provides Arrow native database connectivity to data warehouses, and we've developed partnerships with companies like Snowflake to build those and make sure that high-speed connectivity to those systems is really high quality and can become ubiquitous so that we can start thinking about connectivity in a more Arrow native way across different systems. And so, we envision a future which, is getting here faster and faster where, each part of a distributed data processing stack is made up of reusable components which are connected together through open protocols, and that we can work on as a community on optimizing and improving the different components of the stack so that we build something that is so much more powerful than what we could create building a traditionally vertically integrated system. So one thing that's been happening, more recently that's really exciting is the use of modular execution engines to retrofit older systems with new Arrow accelerated computing. And so, we're seeing already a number of projects. So just Apache Data Fusion Comet was just announced as a project led by Apple to accelerate Spark with Data Fusion, which is an Arrow native query engine that we incubated within Arrow and just spun out into its own top-level Apache project. Meta is accelerating Presto with Velox. Intel and collaborators are accelerating Spark with Velox. So this is very, very exciting. But these kind of new protocols and standards aren't replacing necessarily the existing standards, but they're providing a new fast path that can accelerate and simplify connectivity on the client side, as well as simplify and streamline serving massive data sets out of data warehouses and databases. And so I think there's huge potential here, and I'm hopeful that this will get increased rate of traction within the database and data warehouse community. So this idea of, we're starting to talk about like these composable data systems. So what does this mean? And so by this, we mean that we're building systems around open standards and protocols, and that where possible, we are trying to leverage and design things in such a way that we can achieve modularity and reuse and interoperability. And so by doing that, we have better interoperability, and ultimately we have a system that can hopefully take advantage of all of the advances that are happening at the hardware level in a more seamless and productive way. And so we're deliberately resisting the vertical integration that we've traditionally seen in the past. And so one of the big, areas of thinking as we build these systems and we start thinking about, specialized systems, some systems really excel at smaller scale data, below a terabyte. Some systems excel at the, mid, single digit terabytes or tens of terabytes. And some systems, really excel, at even larger data sets. And so as a user, why should you be locked into using one execution engine for all of your workloads? Why not? You should just be able to choose the engine that makes the most sense for what you're doing. And ideally, you wouldn't have to rewrite your code. If you go from working with a really large data set to a more modestly sized data set, you want to be able to do that transition in a more natural way without having to rewrite your code, that you just say, oh, I'm actually using this smaller scale execution engine that runs on a single node rather than this large scale distributed execution engine. And so we started talking about this idea of a multi-engine data stack, and many people have commented, well, SQL helps with this because SQL is a standard and you can just write SQL queries, and you've got different SQL engines that run at different scales. But one of the problems with this is that SQL dialects aren't portable in practice. There's lots of little differences between different engines, particularly when you start looking at nested types and user-defined functions and all the different function names and different features that SQL engines support. There are some tools that help with query transpilation, like SQLglot, which is an amazing tool for Python, but it's still a pretty tricky problem. And also deciding what engine to use is non-trivial as well. And running the engines is also, different systems have different infrastructure and orchestration requirements. And so that's a lot of complexity to take onto your plate if you're just a data engineer, a data scientist, a machine learning engineer trying to, get your work done. So one of the things that the project that I started around the same time as Arrow, because I knew that this was going to be a problem in the future, and that in the last few years, like we decided to make a large investment in this project at Voltron Data, is Ibis. And so this project, some of you may have heard of it, some of you may have not. It's been a little bit of like under the radar for a number of years, but it's an effort to harmonize the best ideas of modern SQL and relational algebra with the friendly Pythonic fluent DataFrame API. And so it's partially an effort to build a better DataFrame API that doesn't have a lot of the rough edges that the pandas API has, but also to give you the full power and expressivity that you get with modern SQL. And so in addition to making the Ibis API and the Ibis stack like able to solve like a broader and broader breadth of problems, we've also been investing greatly in interoperability and support for a wide variety of backends, which include, both batch computing and streaming execution use cases. And so this is, so the idea is that you write Python code, you get to use a composable kind of fluent functional API for building complex queries, and then you ask this expression that you get at the end to execute against your backend of choice, and based on what backend you select, it will generate the appropriate SQL query or the appropriate polars expression or pandas expression to execute that query. And so we're really excited about facilitating this transition to working with a multi-engine data stack, where at the small scale you can use polars, you can use DuckDB, you can use pandas as it makes sense. But as you start scaling up, that you can transition to using systems that scale and that also can leverage hardware acceleration. So at Voltron Data, we've been building state-of-the-art distributed hardware accelerated computing engine to be able to provide the full capabilities of what the innovation that we've seen in hardware today in a Python API that's accessible through Ibis. And all of this can be tied together because we have Arrow at the API level, we have Arrow for wire transport. And so to be able to sort of put a box around these different systems, say, okay, I don't care what you do as long as you serve Arrow results to me and your API is Arrow. And I know how to send query expressions to each type of system, that we can move very quickly towards working in this multi-engine data stack way. So Anyway, I think I kept to my 20 minutes that I gave myself, but a little bit of context for the rest of the conversation. But as you can see, I mean, I've been working on this stuff for such a long time, but it's 16 years in. I'm as excited as ever about where where we are and where we're going, and we've made a huge amount of progress in the last in the last 8 or 9 years. I think Arrow has been a huge catalyst for innovation and has brought together developers that really hadn't collaborated in the past. And so I think the sky's the limit going forward. So a lot of different interesting problems to solve.
Thank you so much, Wes. So we're having some very spicy discussion right now on Discord because apparently we need more DPT people to defend SQL. So anyway, so thank you so much for the
Uh,
presentations. We received so many questions on both the registration form and also like from the Discord and also like just from in general email. So one thing before we go into like very difficult questions, we're gonna start with something light. Where are you calling from?
um, I'm in where am I calling from?
Yeah.
Yeah, I'm in my office here in Nashville, Tennessee.
Oh wow, this is a very interesting tech hub. So on the things that you have worked on, which one are you the most proud of?
Um, That's tough. I think I'm most proud of Arrow. I mean, I obviously, Pandas in terms of number of users and name recognition and what people know me for. I think um, you know, Pandas is a lot better brand and name recognition, but I think Arrow has had a lot broader and bigger impact in terms of how it's changed more broadly computing and how people are thinking about building data systems, and has essentially changed the nature of collaboration in open source. A lot of these open source systems where it used to be that people would have to build custom connectors or think, well, I want to build a bridge between this system and that system, and now the bridge can just be Arrow, and so that's made things so much simpler and has enabled now there's a lot of companies that are building new novel data processing engines using these off-the-shelf components. There's tons of startups using Data Fusion as an execution engine. And the fact that Data Fusion can take any Arrow stream from any system that uses Arrow and run a SQL query on it is super powerful. And DuckDB can do the same thing. And so yeah, I think in terms of it enables all of these things to happen that would not have been possible, probably, maybe would have been possible, but in a different with a different approach that might have been a little bit more circuitous. And so yeah, I think it just makes the future a lot more interesting. So
You surprised that pandas got so popular?
uh yeah, I would say so. I mean, I think the feedback that you get as an open source developer is heavily delayed. Like the work that you're doing today, it's not going to be recognized and appreciated for easily 6 to 12 months. And so I'm always telling um, other open source developers, hang tight, and just if you're not getting the kudos that you think that the kind of recognition and approval for the work that you're doing, it takes people a while to pick up and install the new software and test it out and really see the value of it. And so I think um, when pandas really started to get like just crazy popular, like I wasn't working day to day on it, and so it was a little bit of this like cognitive dissonance, like, oh, I haven't been working on that lately. Like Jeff Reback is working on it every day. You should tell Jeff Reback how awesome you think he is and the work that he's doing. So I mean, I didn't expect Python to become as popular as it is as a programming language. Like I thought it would be like a mainstream language, but I didn't think it would become like the language of data science.
So more harder questions. Do you think that people should continue using pandas in the future?
Yeah. I mean, Pandas is I mean, it's a very large project. It has enormous amounts of functionality. And I've been keeping an eye on the polars community. I know a lot of people are switching to polars from pandas, especially if they're working with larger data sets or they need like lower latency execution. Polars can be 10 to 100 times faster than pandas in some cases, especially if you have a machine with tons of cores, because it's really good at taking advantage of multi-threading. But one of the things that I think polars has done well is that it hasn't tried to emulate the pandas API, clone the pandas API. It's made improvements over the pandas API in terms of you can express complex aggregations and things that are more SQL-like with polars. But I think Richie and co have kept the polars API a lot smaller and simpler than pandas. And I think in retrospect, if we could have done pandas all over again, I think it would have been better to create like a pandas core and then have like many pandas add-on libraries rather than one like super project that is just, hundreds of thousands of lines of code. Because, whenever there's like a bug in like the HTML formatting in pandas, you've got to wait for a major release, but you might be getting, some changes that you weren't ready for, or like that you don't, that, maybe some behavior changes that happen in the project. So, yeah, I think pandas is not going anywhere. I think it's going to continue to be, even for people that are using other projects like polars and DuckDB for heavy data lifting. I think pandas will still be there as the Swiss Army knife for problems that don't that aren't solved well in terms of aren't solved well with those other tools. Pandas has really great support for time series data. A lot of systems don't support time series data that well. So if you have a lot of time series, you'll probably still be reaching for pandas.
Thank you. So we have a question from Mayang Anand. So the question is, sometimes it can be very difficult to decide which library is the best for the use case. So like among the pandas, polars, DuckDB, and then Ibis. Do you have any advice for people who are trying to make this decision?
I think it really depends on the context that you're working in, who you're working with. I think often people choose tools on the basis of shared skills, like what other people understand how to use, or maybe they choose tools based on what ChatGPT knows how to use really well. Turns out that ChatGPT is really good, and LLMs in general are really good at pandas because of the enormous amount of pandas content that's available on Stack Overflow and on the public internet. And comparatively, the LLMs know a lot less about polars. So if you need to solve a problem and you want LLMs to help you, you'll get a lot better help in general if you're using pandas. But I think I'm encouraging. I see Philip Cloud, who's the lead developer of Ibis. We're encouraging people if they to try out Ibis, and particularly if they're coming from a more SQL oriented background and they have a familiarity with writing advanced SQL. I think Ibis is a real breath of fresh air that have been stuck writing 100 or 1,000 line long SQL queries, or they need to make a slightly different version of a query that they wrote last week, so they copy and paste the large SQL query into another document and then they edit it, or maybe they make a Jinja template for it. I'm not hating on the DBT folks. Like I love all data tools, but I think in particular making it easier for people to incrementally build reusable code, to write functions, to use software engineering practices. Like you can write unit tests for Ibis expressions. It's kind of crazy, but you can do it. So I think to make analytics development and advanced query development more software-like, that was a big goal. Like a big goal with Ibis. But you're not stuck using, any one tool. So there's plenty of people that use Ibis for a lot of things, and then they write DuckDB SQL, to do other things. And so you aren't forced to, just use one tool. But it's nice that, you can deal with Parquet files everywhere. You can deal with Arrow data everywhere. And so at least like moving the data around is not as painful as it used to be.
Um, So we have another question from Thierry, now that you mentioned Ibis. So Thierry from DACWorks, his question is, with projects like Ibis, Narwhal, DataFrame Interchange Protocol, Array Protocol, how close are we to a truly unified DataFrame interface? And what would be the last mile that we need to get there?
The Trying to think, see what I can find. The I think I'm not. I mean, I'm not maybe not familiar with um, what you're referring to. So I know there's an effort to. There's been like an effort to build like a standardized data frame API for Python. Is that is um
Yeah. So I think his question is just like how close we are, like to get like truly unified interface.
it's I think we made a lot of progress. There isn't consensus about there isn't necessarily consensus about the right path forward or like what should the API look like. I think there is a school of thought that the pandas API should be cloned as much as possible because there's so many people know how to use pandas, and so if you um, you know, so if you build like a pandas emulation layer, this is the path that Modin took, and the company behind Modin, Ponder, was acquired by Snowflake, and so Snowflake is now working on a pandas API emulation layer for Snowpark, which is their kind of sort of Python API, like similar to Spark data frames and so forth for Snowflake. So there's different. I don't necessarily think there's going to be one API, one ring to rule them all. But I think there's good ideas, good ideas in Polars. There's I think Polars and Ibis have taken a very similar approach, and the API is the API is very similar, subject to some slight name changes or syntactic differences. But I think where possible, we've tried not to diverge too egregiously, or if we make changes or we do things differently, that there is a good reason for doing so.
So when I was looking at the question from the audience, I was surprised by how many questions about accelerated computing. So there's a lot of questions about like now that with on the GPUs coming out, TPUs, like how would those hardware change what data engineering interface or tooling?
Yeah, well, I mean, with GPUs and and NVIDIA GPUs in particular, because NVIDIA has the highest quality, the best software suite for CUDA for programming on GPUs. I used NVIDIA GPUs for statistical computing way back in 2010, if you can believe it. But it was still CUDA back then, and even back then you could get for certain statistical workloads, you could get 100 times speed up over what you could do on a modern CPU. So there's a lot of, and Moore's law hasn't ended for GPUs either. So the core counts and memory bandwidth and the performance that you can get out of GPUs has continued to continue to go up and up. Whereas CPUs by comparison have comparatively stalled out. Maximum clock performance hasn't increased, has not continued to increase, like Moore's law originally predicted. But the thing is, developing for GPUs is really really hard, and so you need it requires deep technical expertise to understand the kind of low level networking, memory data transfer, how to write really good CUDA kernels. There's really subtle things that can happen on GPUs that result in poor performance, and I have kind of psychological scars from poring over CUDA prof outputs to try to understand how I could change the memory access pattern of a CUDA kernel to get the performance to be 10 times or 100 times faster, because it was doing I was doing GPUs the memory access wrong. So it's a lot harder to get to get the full potential out of GPUs, computing, memory access. networking. And so I think that's a big part of why this composable data systems approach of like having everybody collaborate on really high quality components for GPU execution. So like libraries like Rapids, cuDF, which provides accelerated computing kernels for CUDA, and projects like UCX, which provide an abstraction layer that deals with the low level networking of like, well, how do I do direct memory transfer from this CPU memory over here to this GPU memory over there with minimal overhead, or do direct over InfiniBand, move data from the global memory of this GPU to the global memory of this other GPU on the network. So fortunately, I think developers, have collaborated to build software projects that are addressing these problems to make it easier for people to build high performance applications that do analytics on GPUs, because it's just not practical for everyone to have to become get a PhD in computer engineering for GPUs.
Was some so like recently we hosted a GPU automation workshop and it was like shocked by how much interest there are about like GPUs programming. So it seems like a lot of people are looking into that. One thing you said that I find very interesting is that like you said that CPU performance can just like hit like reach maximum they can't scale at a certain point. What does a point look like?
I think maximum core like clock speeds on individual CPU cores have been topping out at 5 GHz plus or minus for a number of years, and I think CPU manufacturers have been responding to this by fabbing I think core CPU core sockets with a lot more cores on them. So I mentioned that the latest x86 server processors have 96 physical cores on a single die. I believe in the ARM ecosystem. I don't know what the maximum number of ARM cores you can get on a AWS Graviton or another custom design ARM processor out there. I know that the latest and greatest like M3 Max processors have a lot of cores, so they've got CPU cores and GPU integrated on the same die. I know that there's a lot of the work to make modern CPUs faster has come via better memory bandwidth, and that's part of the reason why Apple Silicon has such great performance, because they've really worked hard on the memory bus and like getting better memory bandwidth to the cores, so that you don't end up with this like CPU starvation um, problem of not being able to deliver data fast enough to the CPU cores. And I expect that with the next generation of CPUs, RISC-V, that we'll see continued trend and kind of increases in CPU core counts, as well as better and better high bandwidth, basically much larger caches and high bandwidth memory that's available on the CPU. I don't know if anyone's familiar with CXL or chiplets. That's another trend in computer engineering to basically be able to build servers rather than having a rack of like where every blade in the server every blade in the server is a different computer, and you have to coordinate them through networking. But instead, you can have an array of chiplets, and so you could have a single logical computer that has thousands or tens of thousands of cores and enormous amounts of high bandwidth shared memory to build computers that are an order of magnitude larger in terms of the number of core counts and the amount of memory available. And so you can think of them as like really big single nodes. And so when you have systems like DuckDB that are only saying, well, we're not doing distributed computing, we're only doing single node computing. When the single nodes keep getting bigger, I think that's very interesting, because in the future, a lot of people have data warehouses that only need one machine to process any query that they might run, and so to use the distributed they may never need a distributed data warehouse if they can do everything on, one really big server.
Yeah, so when you said about that, I remember about what DuckDB. So I think there's a lot of people like argument. It's just a vast majority of data workload can just happen on one machine. Do you believe that?
I mean, there's a if you look at if you believe the data that's coming out of cloud, cloud data warehouses or anecdotal data, there's a lot of customers that customers of these systems, users that that don't have petaScale warehouses, or maybe they have big data. They might have petaScale warehouses, but it may be that the window of data that they're analyzing at any given time isn't that big. And so if 99.9% of your queries are never touching more than a terabyte of data, it may be that you could achieve better performance by doing distributed computing, but you have to remember that distributed computing introduces overhead because of communication overhead, coordination, data coordination across nodes. Of course, with fast networking and better software to make it easier to use, um, leverage fast networking. That overhead is definitely going down. But you can you know, like I was saying, a single machine, two sockets with 384 physical cores, that looks a lot like, some of the, 100 node commodity clusters of 15 years ago. And so things that were distributed computing problems back then, now can be done on a single node. And obviously, I'm oversimplifying a little bit, but yeah, I think you know, I think if yeah so I'm interested in that. We'll see, we'll see what happens, but big data does exist, and people should also have high performance, hardware accelerated systems to be able to tackle those truly large scale, above 10 terabytes. Like, we need systems that have significantly lower carbon footprints, that are just a lot more computationally efficient to process data at that scale. And we're clearly getting that through GPUs, and eventually through custom silicon.
So it sounds to me that like it's a matter of whether which one grows faster, the data scale or as a capacity of like a single node.
Yeah. So you need both. And so I think to say like we can only use one or the other is a little bit of a false dichotomy. But to be able to work, to have ubiquitous, ubiquitous, scale up, scale down, single node computing with whether it's polars or DuckDB, or there's in a data fusion, there's different single node engines that are being under in active development. But when you cross over into, and it could be that your query optimizer is deciding, well, I looked at my statistics about your tables and I see how large the Parquet files are in your data lake, and I know that you need, if you want to deliver the results of this query within a certain time frame, if you really care about time and latency, then you need to use the scale out engine. And so to build in a way that you can seamlessly say, okay, I have big data in this query and this other one I don't, but it isn't a great hardship where you have to really seriously change your workflow to be able to move between those different environments. So we're not there yet, but I think the right pieces are being built to make it all possible. I think for people to have choices is great, and to just use the tool that meets your requirements, whether it's like keeping costs to a minimum, or having the best performance. And a lot of companies are, very, very carbon conscious. And so maybe that, in their data warehouses, they're going to make optimization decisions based on just power utilization. And so choosing the system that, making decisions that minimizes the amount of kilowatt hours that they consume is their objective function. So I think that we'll see all of those things. And I think as data system engineers, it's up to us to make that possible, so that the users can make informed choices, and and pick the systems that that serve their needs the best.
So it's like there's so many things going on from all directions, right? From hardware, data formats, storage, query engines. So what are some of the biggest challenges or like biggest problems that should be solved for the engineering data system today?
Uh, it's a big, it's a big question. I mean, I think that the general trend of like modular components, that these modular systems, it very much parallels the change that has happened in the semiconductor manufacturing space. And so, if you think about the way that computer chips used to be designed and fabricated, Intel designed their own tools. They design their own chips. They fab their own chips. Like they it was a vertically integrated design and manufacturing stack. And with NVIDIA, now the most valuable company in the world, and the ecosystem of technologies that has enabled that to take place, it's it's a horizontally integrated stack where you have ASML in the Netherlands specializing in um, cutting edge photolithography, and they've got optics manufacturing. And I think Zeiss might make them, or it's an optics company in Germany that provides optics to ASML. And there's companies like Cadence Design Systems, which build the software for designing semiconductors, and then TSMC takes the semiconductor designs along with the photolithography and all of the things that TSMC depends on, and they can fab 3 nanometer chips at scale for the world's needs. And so if NVIDIA needed to solve all of those problems themselves to do their own photolithography and their own chip design, and they do their own chip design, but all the tools and software and everything. So the vertically integrated approach, you can see what's happening in the market, that the results are clear, kind of like what the future is going to look like. It's clear that having hyper specialization in building these different components yields, in the fullness of time, a much better outcome, because you have specialists working on making the different pieces of the stack as good as possible. So to build all those things and to make them all work together is a lot of additional work, because you have to have coordination, you have to design the interfaces and protocols, and you have to enable people to take those off the shelf components and fit them together. But I see the challenge that we have in the data system space as being very, very similar, in a sense. And fortunately, the work is happening. We're seeing kind of these modular execution projects. People retrofitting Arrow into their systems, adopting these open protocols and standards, having open data lakes. We talked about tabular at the beginning of the call. Having an open standards for data storage, large scale data management, data lakes is essential to enable this interoperability, and that's part of why you see kind of some of the biggest players in the space, like Databricks and Snowflake, to be competing for mindshare kind of in that space. So whoever I think we'll see data lakes built on open standards, but who operates who operates the open data lakes also serve as a rent collector, and that's very profitable. So it makes sense why Databricks wants to be such a major player, and having such a major role in the development of open data lakes. So it's a very interesting time to be in the space, and I'm excited to see where things go.
Thank you. So we actually have like 6 more minutes. So I'm gonna ask a lot of like rapid fire questions. Hope it's okay. So one thing, what are the essential data science skills or data engineering skills that you think people should be learning right now?
Um, well, some people on the Discord are going to laugh, because I'm going to say that like learning SQL is actually a really good skill.
You're not
I
a
think
fan, I like Philip a lot, but okay.
Well, I think that it's not just learning SQL the language, but learning the concepts of relational algebra and how to think about how to think about data sets and designing schemas, organizing data. I think beyond like relational algebra and knowing how to use data execution engines, data warehouses, SQL engines, both the large scale hosted and the kind of embeddable, local, um, like knowing how the like file formats and like the basics of data storage, data partitioning, because there's often a relationship between how the data is stored and managed and how well the systems like DuckDB perform. So I don't think you need to be an expert in administering iceberg tables, but having a general idea of what these tools are good for and what are some of the general the basic things like relationship between the execution engines and how your data is stored. And I think all of these things will enable you to be a better DBT user. They'll enable you to be a better Snowflake user or a Databricks user. And so because ultimately it might seem, kind of it's like the wizard behind the curtain. I think I think a lot of these systems have a very similar architecture and properties. And so this help you have a better understanding of like how these systems work and how to use them effectively.
So there are a lot of new challenges, but like what is the one question that you're thinking of right now?
What's one question that I'm thinking about?
Yeah.
Um, well, a bunch of us have been the last few years. A lot, we a lot of us have been thinking about how to continue innovating in the space of columnar file formats, especially people like me I didn't design Parquet, but I've worked a lot on Parquet implementation, and I recognize that our we have these open data lake standards like Iceberg. They use Parquet as a storage format for individual files, but in principle, Iceberg and other systems are not limited to using Parquet. And so it's important that we continue to make Parquet better and make the Parquet implementations better. But for different applications, especially now that we have Arrow as a kind of API standard and an interoperability standard, that we can start thinking about really great storage, like new storage formats that are designed for use with Arrow, and that simplifies a lot of the implementation work. You can say, oh well, we assume that anybody using this file format is going to be using Arrow, and so that does make things simpler for people like me, working on implementation. So,
Yeah.
I've collaborated the folks that I worked on the composable data systems paper at Meta. They just open sourced a new file format called Nimble, with a bunch of interesting ideas that partly developed within the Procella group at Google. They built a proprietary file format there called Artis, and some of those ideas are represented in Facebook's Meta's Nimble format. I think that's very interesting. A bunch of database groups like TU Munich has a paper called Better Blocks, where they've done research on columnar data encoding. CWI has some really interesting research called Fast Lanes about SIMD accelerated columnar data encoding and decoding. And so I think there's a lot of opportunity for the academic research community to collaborate with industry to continue to innovate in this space and to make everything work really well within open data lake standards like Iceberg. So I'm not working on anything concrete there at the moment, but it's a problem that I'm thinking a lot about.
So like how does a columnar data format work with unstructured data?
Um, it's It depends. It depends on how big the image is and other like text or unstructured data is. Like we see with like when people we see people storing unstructured data in Parquet, where every image or like every blob goes as an entry in a bytes column, binary column. If you look at LanceDB, which is a new um, columnar storage project for optimized for AI and vector search applications. They often will allow you to put the unstructured, data in like a separate file, so it isn't necessarily intermingled with all of the standard, string and Boolean and like more analytical columns. And so that enables the unstructured part of the data set to be manipulated separate from the kind of structured columnar, part of the data set. So people are looking at different approaches to this problem, but I admit that I haven't worked on many hands-on applications involving unstructured data, and so um, for the most part, I defer to others' expertise uh, and knowing how to deal with that.
Thank you so much. So it's just a time here. So there are a lot of questions we haven't had a chance to go over. So like for the audience, if there are questions that we haven't been able to get to, feel free to post them on Discord. So and we can try our best to like, get there. So thank you so much, Wes. Really appreciate your time today.
Thanks for having me. Thanks for joining.